Hi, everyone, and welcome to today's session. So today we are honored to have Leo as well as Marius to join us to present on their symbolic AI architecture. So actually, I met Leo on the Machine Learning Street Talk Discord, and we were talking quite a lot about all these latest technologies in AI. And I'm very excited about his work because it combines the current trends of large language models to interface with some symbolic tools. And so this overall framework is called a neural symbolic framework. And I'll leave them to introduce you how it works. So just some brief introduction. Leo is currently an applied scientist for Amazon devices. His main expertise lies in the field of deep learning, and his most recent focus is that of large language models. As for Marius, he's currently working as a senior AI research scientist at Atlas, and also is a PhD student at the Institute of Machine Learning at Johannes Kepler University in Linz. His main expertise lies in the field of deep reinforcement learning, same as me, domain adaptation, and the study of neurosymbolic AI. So first up, if you haven't already seen their repository, this is the Symbolic AI repository. And this, basically, you can see from this little clip over here, you can use it to express things in symbols, and you can use the symbols to do many things like translation, extraction of, and search the web, SQL queries. In fact, it is interfacing the large language model's input of this to extract and use the relevant tools, symbolic tools, in order to fulfill your requests. All right, so without further ado, I shall hand over time to Leo to describe more about the architecture. Okay, Leo, please.
Hi, everyone. Can you hear me?
Yep, loud and clear.
All good. Okay. Let me share my screen. Can you see it?
Yep, E to the power AI.
Okay, so we were thinking to have two parts. I will do like an introduction part in which I will talk about maybe some theoretical aspects and why we were developing this framework. And I wanted to give you some motivation and intuitions into some of these underlying concepts. I will have to say sorry in advance if I would probably go very fast over some of them. But if you have questions, please note them down or we will have a Q&A session at the end, and we can discuss them if there is something that won't be clear. Yeah. Okay, so why solving language? A lot of people might ask why solving language is kind of important. So in a way, because the limits of my language mean the limits of my world, which is a quote from a famous philosopher, Ludwig Wittgenstein. And it's something that resonates deeply with me and with the current zeitgeist that all of us are seeing. So to ground you with an example, I just want to ask you to imagine something that probably happened to all of you in your current lifetimes. Probably it will happen if it didn't happen already, which is the fact that at some point we might all be a tourist in a foreign country, right? And you don't speak that language and you don't understand it. So how would you communicate and speak with another person, given that you do not understand and speak his language, and he might not understand the language that you speak into? So as you might see easily the problem here, and it's something that very often happens even if you're trying to learn a new language. And this issue that we are seeing here is coming from the fact that we are usually trying to understand a new language through our own native language. So we are doing some sort of translation in our head. We just move back and forth between the two languages and we root it in our native language. So if you think about this, this translation, you might be able to find out, and there are people who study this. There is a philosopher by the name of Quine, which in his thesis, which is called Word and Object, he discussed a very important problem of translation, which goes by the name of the indeterminacy of reference. And what he meant by this is that there is no way for me as a speaker that is trying to understand your language, there is no way for me to come up with all the possible interpretations that there might be for words and phrases and sentences that are taken out of context. And he gave a very interesting example to point this out. He basically asked you to imagine that you are with a tribe of people let's say, that there are a lot of discussion going about the Pariah people, which is a very famous example in the field of linguistics, because apparently they don't speak languages the way we are familiar with. So imagine you are with them on a field and they are suddenly starting to point out towards something, and they are starting to say a word. So you might easily, let's say, infer that that word stands for the animal, right? Let's say it's a rabbit. So it might point to the rabbit, but how are you sure that that's what he actually meant? It might be the case that he was actually pointing towards the act of hunting, and he was asking you to participate in this act of hunting. And this is just one problem that is happening in natural languages, which is this translation issue. There are much more that lie hidden, and without even any effort, you can, even by standing over a tea in town and just think about language, you might start coming up with interesting questions. And one of them, which really caught my attention, and it's probably one of the reasons like I got into this, is how do you come up with the words, right? When you speak, how do they come out? So this is a very interesting problem, because it points towards, it makes an obvious observation if you think about it for some time, and it points to the fact that language seems generative in a way, because words seems to come out. You don't know why they are coming like this, they just pop out, and you apparently can make sentences and phrases and so on. So like you, a very distinguished fellow by the name of Noam Chomsky, in 1955, when he presented his PhD thesis, at that point, he basically tried to capture this this thing by studying grammar. So he studied grammars, and the way he studied grammars and the way he thought about grammars was as being a set of rules, which you basically combine. And by combining them, you are coming up with new sentences, and you can further combine them by taking these existing sentences and making new ones. So this was very revolutionary work at that time. And you will see further down the presentation why. And in 1 year, so 1 year goes by, and he comes up with something that really changed everything in linguistics. And I will show you in the next slide that it's not only linguistics, it's like it's pervasive. It goes even into computer science, and it's a topic that lies at the heart of your personal computers, and it goes from parsers to compilers, and it's in everything. So even if you would build like a new programming language and you wouldn't know at all, you have never heard in your life about Chomsky and Chomsky hierarchy, you would still discover in a way by yourself, because of the guidelines of how you build programming language and so on, you would inevitably go over the same process. You would actually discover it by yourself. So on the slide, you can see that there are some circles, and probably the obvious thing that you might observe is that there is a center, and from that center you can expand outwards. So it's a type 3 grammar, because he studied grammars, And he basically thought about a very simple thing, if you can see it like this. He basically asked himself, how can I come with a very restrictive set of rules, like something that would not allow me to do much, and just build up from there. And this is exactly the type 3 grammar that he initially studied. And all he did then was to remove one restriction at a time. And by removing this kind of restrictions, you just expand outwards towards more general kind of grammars. Okay. I will give you a little bit of a little sneak peek into some formal properties of grammars, which it shouldn't be that complicated to get. That basically a grammar has what they call production rules, and you have to think like a direction. It goes from LHS means left-hand side, and it goes from left-hand side to the right-hand side. What this means basically is that you just replace the left-hand side with the right-hand side. So this is a rule, okay? And these rules apply to non-terminal symbols, which is a finite set of non-terminal symbols. And you also have like a set of non-terminal symbols to which this rule do not apply. You can think about them like a stop criteria. It's when your constraint is satisfied and you will just stop, you will not produce anymore. And it also has like a start symbol, which is part of this finite set of non-terminal symbols. In the way it's standing by itself because it has a more distinguished reputation, because it just starts this whole generation process, and the way you choose the start symbol will define what kind of path you would take in building this kind of grammar. So, because I told you that what Chomsky studied was grammars, and obviously grammars in his case was connected to the study of languages. And his simple idea was, because language was a generative process, he studied grammars, which are the rules of combining words, and by combining words and evolving these rules, you come up with languages, okay? But this is not the whole picture. People, very smart people from computer science has seen an intuitive connection with their field, and more specifically the automaton theory, which is a theory of computation. And they immediately started to do again the same obvious thing. How can I take this grammar, which produces this language, and put it into a computer? This is what they did. And they come up with ways of mapping grammars and languages to computers. And this, as you may think, emerge as programming languages and parsers and compilers and so on. And I wanted to show you a little bit how this mapping and how these tables feel itself. So at the most restrictive kind of language that you can have, as I said, is type 3, which creates regular languages. And a regular language is it's a very simple thing. It's, for example, the set of regular expressions, right? So if you write a regular expression, if you ever wrote a regular expressions are a language defined by the type 3 grammar, which Chomsky studied initially. And this obviously maps to the computation side of things, to a finite state automata, which usually doesn't have any memory, because if you think about it, regular expressions are local. They do not involve the use of any memory. They just happens to be, you just match things, and that's pretty much it. But if you, and I also, there's also some examples here. For example, the left-hand side of this, of the production rule is a single variable, and the right-hand side is either a single word or it's a word plus some variable. Okay, so S here stands for the star symbol, the one that it's the distinguished symbol from the properties of a grammar. With it, for example, you would replace X. So first thing that you would do is to go from S to X. So that's one replacement you can do. You can also do another type of replacement, which is take S and replace it with AX and so on. And then you might have another rule which would tell you how you would replace X or how would you replace A. And you just keep doing this thing and you just evolve them and see what kind of things you can discover. So this is the type 3 grammar. It gives you regular expressions in computer science. There's also the type 2 grammar, which has the name of, which creates context-free languages, which is usually the kind of languages that you might get in computer science. Like, I don't know, many languages are here. Many programming languages lie exactly in this category. And the difference between type T and type 2 is the fact that you augment your automaton with a stack memory, which is a very simple type of memory. It basically implies that you just, it functions by the last in, first out. So if you know the classical Tower of Hanoi problem, it's the same thing. You just remove the first one, and then you have to get to the second one, have to take the first one, and so on. So this is a stack. And the stack obviously has a push and a pop that you can do. So these are the operations that you can do. And the grammar creates these context-free languages, which, as you can see, the restriction applied on this kind of grammars is they are basically taking a symbol on the left-hand side, which is a single variable again, and you can just create a much complicated, less restrictive kind of sentence or production rule, because you can create, you can no longer say that it's a single word to the right. You can make it much more complicated. Then you have the type 1 grammars, which create context-sensitive languages. Context-sensitive languages, if you think about it, you can think about it this way. So context implies that you have to, on the left-hand side of the rule, you would get this rule by only matching let's say the star symbol with constituent elements on his left side, right side, whatever you want. You can do whatever you want. But context is exactly what you would expect. It's like condition. This rule exists given that it has the star symbol and it has another symbol to its left side or right side. And as you can imagine, these languages are less restrictive and are more complex than the previous ones. And they map usually in computer science to a linear bounded automata, which uses bounded RAM, random access memory, which is a way of saying that it's basically your memory from your computer, your personal computer is the same memory. It's a different kind of memory than a push down stack automata, which is a stack memory, because you can access random points and cells in this memory, and it's obviously much more powerful than a stack memory. And by moving one step up, you would reach the type 0, which is the most general type of grammar that you can come up with. It has the characteristic of being recursive, in the sense, recursive in this context means that it can terminate. So you would not go at infinitum with production rule. You will guaranteed to terminate at some point. There are also recursively enumerable type of languages also emerging from a type 0 grammar, which would loop forever. And you have here the famous halting problem that Turing studied, and so on. So this is just like a short and brief picture of what the Chomsky hierarchy is. I just wanted to take the gist of it and think of grammars creating languages and computer scientists coming into this field and basically taking this languages and putting them into a computer. This is the way and the normal progression that you should have in mind when you hear Chomsky hierarchy. This is what it does. But as you would expect, with very interesting paradigm in computer science and so on, this is not the only picture. And there was another person who created an entire field called information theory. He is the father of information theory. It's called Shannon. And he studied language from a different perspective. He was not thinking in terms of set of rules and grammars and so on. He just looked at the frequency and took a statistical approach to developing language. And he beautifully stated in his paper, which is called Prediction and Entropy of Printed English. It was published in 1951. So it was kind of 4 years before Chomsky's work. So like you can think of Chomsky reacting to this whole emergent field of statistical learning and statistical tools in natural language processing. He was reacting to this in a way. So he put it very nicely that you can assume, right, that anyone who speaks a language possesses an enormous knowledge of the statistics of this language. This is without a doubt something that it's true. To what degree it's true, it's something that is debatable, but it's an obvious assumption that you can make about language and how do we use language. And he came up with a game, which is Shannon's guessing game. And the way he thought about it to study it was very simple. He just took a sentence and he just asked you to fill in the gaps. There is also a game, I don't know if you played it as a child. I did. It's called a Hanging Man, where you just do exactly this problem. It's exactly this problem, but you solve it as a child, and anytime you miss a word, then you just draw a hand and so on until you hang the man. Yeah, very peculiar type of game, if you ask me. But we played it as children in my case. So obviously, by studying this, you would come up with the actual sentence. So you discover how the sentence should look like by making guesses. That's why it's called Shannon's guessing game. But when you make guesses, a lot of things are going on. And this was his intuition, that a lot of things should going on here because, as he said, it's not only like, there are not only grammars and things like this. There's also the underlying statistical statistical properties of language, which is how words relate to one another and so on. They are very important to be taken into account. And he discovered something very important in 1951, by the way, that English should have between 0.6 and 1.3 bits per character. So this is the amount of surprise or entropy that you should have for a given English character from the alphabet, okay? So this points to something that I found very interesting, and I was thinking about it like a lot, which is data to information ratio. If you never heard about this concept before, data to information ratio is just a way to study how much data would you need to extract useful information. So for example, in our case as humans, we don't need a lot of examples, right? I show you something once and you can immediately uncover the information. So this is very important. Computers cannot do this very easily. And Marius will discuss more about in context learning and so on. But to the machines, we kind of breach the gap right now. We are narrowing it. But data to information is just a concept that would tell you how much data would you need to extract useful information. And the thing to have in mind here is that rules exist. So the Chomsky rules that he discovered and thought about they exist, but from a practical standpoint, they get drowned by noise. So what is this noise? And I'm giving you here like 2 examples, and the way I think about them. It's on the left side, there is the famous ImageNet dataset. So if you would put your informatic theoretical lenses and study this subject from this point of view, you would very easily start to find out that by having 1,000 classes in this data set, you would basically, but implicitly, by the way this data set was designed, you would get only 10 bits of information per class. So just imagine this. You have all those billions of pixels per class, right? For each images from a specific class out of the 1,000, you have billions of pixels, and you only need 10 bits length long binary number to encode all this information. So as you can see, it's a huge, it's a high data to information domain, the image domain. And the same things apply to, for example, to language. Take these numbers with a grain of salt. I don't expect them to be actually accurate, but it should be right there. I mean, they should come up right around this number. This is, for example, for GPT-2, and this Wikitext dataset has 20,000 Wikipedia articles which were curated and cleaned and so on, and they found out that actually the amount of information per character is roughly 1 bit. So if you think about words in English, they would have like an average of five characters per word. So that would be like 5 bits per word in the English, given this data set. So as you can see, it's a huge data to information ratio. And this is exactly why these models, like the ones that we are building in deep learning, are so good. That's why you would never be able to design, even though they try and they failed in the 80s. That's why it's not possible to design rules, to capture all the rules of how you distinguish one class from the other. So this is why deep learning shines, exactly because there is a high data domain. And even though the information is relatively small, you can still recover it. There's also a lot of redundancy in the English, for example. I bet you can all read this phrases, and this only points to the fact that you don't need much to read. You just need like the first and last word to be first and last character to be in the right place, and then you can mingle around with what's in between, and you can actually read it. Your brain is like is doing this self-correction. And if this would have been a live session, I would have asked you how many of you think that GPT solved this kind of problem, but we are not live. So I will just tell you what happened in the last session that I held. So they were skeptical about if it solved it or not. But not only it is solved, it can actually give you the answer exactly like this. So it understands this specifically this problem. You can test it if you want. So ultimately, this is a story about statistics. It seems that it's all statistics. With ChatGPT and all these emerging generative models, it is all statistics in itself. So in a way, it's all Shannon all over the place, less Chomsky and a lot of Shannon. But is it clever statistics? I would ask. And the answer is obviously not. It's just a very raw and basic way of doing statistics. You just predict the next word or the next token in this case. And I very much like this quote from John von Neumann, which said that with 4 parameters I can fit an elephant, and with 5 I can make him wiggle his trunk. What he tried to convey with this message is that in physics, if you would go with 4 parameters to your to a 4-parameter theory or model to your professor, he will just tell you to choose another professor. He won't work with you anymore, because if you take a 5-order polynomial, you can very easily overfit the data, and you can fit whatever you want with an order 5 polynomial. Now, deep learning is exactly the reverse of this. It's actually billions of parameters to fit an elephant. So it's not only 5, they use billions. So apparently it's useful to use this kind of thing. So John von Neumann, even though it doesn't apply in physics necessarily, it had a point which the deep learning domain proved it wrong, that where there is high data to information ratio, deep learning is very good, and you should have a lot of parameters. You just scale the models up and so on, the data set, and you just do better. So there is this thing which was discussed by Julia Pearl, and if any of you took any course in Bayesian statistics, the first thing you will find out is, if one thing the professor will only tell you is that causes don't lie in the data, and you as a scientist should study the implications of the data by building causal graphs and checking by wiggling one parameter, how does your data respond to it, and so on. So this book, The Book of Why, I highly recommend it to everyone. It's a very interesting book because he came up with this ladder of causality, which and on which we are currently only on the first level, which he called the association or the seeing level. So you just look at the data, which is exactly what models currently do, and you just create associations, correlations, and there's nothing causal there. You just look for patterns, and that's it. Now, if you want to build more advanced things like we humans do, and the Bayesian statistics is one of them, is you can create interventions. As I said, you can build a causal graph, you go in, you just wiggle a variable, and you see how data responds to it. So this is a very powerful technique, which the current AI models don't do very well. Probably there are some who do, and with the advent of GPT-4, they will do some of these things, but don't expect this to happen like over the night. It's a very hard problem. And the next ladder, which he was thinking about it in terms of creativity and where our faculties of reasons lie and so on, would be this domain of counterfactuals, which would just be asking yourself what if questions. So you not only modify your graph, your causal graph, you would go beyond this causal graph, and you would actually ask, what would happen if I would put one more variable into my graph? How would the data change? So you can change this initial graph behavior by putting additional parameters to see how exactly this whole data set that you have would react to it. So this is the domain of counterfactual. So I would say as a conclusion that it's not clever statistics, it's just the dumbest way of doing statistics, but it just works very well, apparently. As you would expect, and there is this very interesting essay wrote by Peter Norvig, which I highly recommend to read, and because it summarizes the points of Chomsky and the points of the statistical culture people, and you can see exactly where things might go wrong and so on. And as you would expect, obviously there is a clash between the two domains. As I told you before, Chomsky had a reactionary work, and he came with a response to these statistical models. But I won't go too much into it. I just wanted to mention it. It's a very interesting read. Just give it a try. The last thing I want to talk about before giving it to Marius is what is a symbol. And as you can think, one way to think about it is a symbol evolving in time. So this would show you, for example, on the left-hand side is the evolution of the English alphabet, and you can see how it evolved through time. So you can just by looking at this, you can see that obviously symbols change a lot, and different events in times and different historical contexts will give you a different meaning to a symbol. So symbols obviously change. So whatever you do right now with your transformer, you would only capture the meaning up until this point. If I would ask you to do the same thing over 1,000 years, in 1,000 years, a lot would have evolved in terms of how language, probably a new language will come up and so on. So you would need to, if you would have the same tools as today, you would just have to retrain everything and just put those 1,000 years into your models to get this out of it, because it's not in. The current models don't have this. And one interesting definition of symbol is that they are entities that mean something to someone. It's a very practical definition of symbols, and it's one that you can work up with. And you can basically define a symbolic behavior on top of the symbols, which have some properties. For example, I listed some here. For example, a symbolic behavior should be should exhibit receptiveness to you, should appreciate conventions and receive new ones. It should be constructive for new conventions. It should be embedded. So you should be part of a broader system and contribute to the system that you're part of. It should be subject to change, obviously, as you can see on the left-hand side in that graph. It should be meaningful, so it displays semantics. And not only display semantics, you should use those semantics to actually explain why did you came up with the semantics. So it's a very interesting characteristic of semantics, that you can use it to explain what semantic is. So it depends on itself in a way. And obviously it's graded, right? I mean, there are no binary things. Usually, I mean, there are, but you should never assume a thing is binary and start from there. You should always, probably in the back of your mind, have something like a more fuzzy system. And graded here just means how, for example, would you grade ChatGPT? And you would see that ChatGPT is graded by looking at how good is it with math, how good is it with creative writing, and so on. So, sorry, okay. So I put this on the right side of the properties. So where do I think current large language models, not only me, because I had inspiration from this DeepMind paper, which I also recommend to read. Obviously, they have receptiveness. So this is the strongest point right now. They just take into conventions and very easily receive new ones. If you do in context learning, you can give it new conventions that it should adhere to, and an instruction is a way of receiving new conventions in a large language model. Are they constructing and subject to change? No, I would say not at all. They don't form new conventions, and they do not change. They don't understand how a meaning change. You can do things, and Marius will explain when it will explain our frame, when you will see the power of neurosymbolic approaches in this case. But obviously they are not malleable and constructive. Are they embedded, meaningful, and graded? Somewhat, yes. It's a maybe. It's a big maybe. Graded, kind of more towards yes, because they evaluated the system over mathematics, language, creative writing, how well is this toxic, is it, and so on. It's not binary. You are not asking, is this a good sentence or not? You are really looking into much more than this. So is in a way graded, but it doesn't come with its own goals and things like this, which would make it fully graded to properly evaluate itself. We've seen some recent work into this direction, but we are not fully there. And embedded and meaningful, I would say it's again debatable, because apparently just capturing syntactic rules, it's giving you a lot. So there is an argument in the research field of computational linguistics, in which people came and said that large language models are just stochastic parrots. So they just reproduce and come back with an answer. But it's clearly that by no means you evaluate their hypothesis, but it's obviously it's much more than that, because capturing syntactic rules like in grammar in itself apparently seems enough to come up with meaningful sentences and so on. So they lack something in their hypothesis, and this is very important to be taken into account. Now, how would you use a symbol, for example? And a huge inspiration for us was this paper, which is Search and Reasoning in Problem Solving of Herbert Simon, which was published in 1983, in which he discussed this triad of three different elements, like how they combine together. And he came up with a thing that he called symbolic structures, which would define your search space. And this symbolic structure, you can think about them as nodes, and you just traverse this space that you created with the symbolic structures. It also has reasoning, and by reasoning, he meant more towards the formal language kind of things, like context-free, context-sensitive, and the ones that I discussed before, in which you have axioms and you can build expressions. And also, another point that is very important to him is the one about constraint satisfaction, which is a way to narrow your domain when you are searching that huge space. So he said in his famous Turing Award lecture together with Alan Newell that symbols lie at the root of intelligent action. And not only this, he actually went further and said that the symbol may be used to designate any expression whatsoever. So with this in mind, I just give you a last thought from the famous Judea Pearl, and this thought is that you cannot answer a question that you cannot ask, and you cannot ask a question that you have no words for. So without further ado, I'll give the mic to Marius to show you how do we use symbols and where do this come into play.
Thank you. Have to stop sharing, I think.
Yeah. I just don't see it. Where's the pop-up?
You have to click on the stop share button.
Yeah, but it's not here.
Okay. Let me just force stop share. All right.
Yeah, for stop share. Yeah.
Okay. Give me a while.
Okay, perfect.
Thank you.
All right. Yeah, that was a very
Thank
good
you.
theoretical introduction to what's a symbol. So now Marius will talk more about the symbolic AI framework. So please go ahead.
Thank you. You should see my screen like in full screen, right?
Somebody.
I think someone is turned on. Thank you. So you should see now my screen symbolic AI framework, right? And nothing else. Yes, no, someone?
Yep.
Okay, thanks. So thank you, Leo. And now, well, one of the things that you probably also followed up on Twitter and was hilarious always to watch is like the perspective of end-to-end learning and just statistical driven part, like that's enough, just scale up the data, scale up the models. Or on the, like in the past, it was, you know, in the 80s and so on, we had these things where we want template-driven development. So we had like always abstraction and trying to find more and better abstractions such that we can, you know, solve more and broader tasks. So in one ballpark, on the one side, you had the software engineering approaches up until the 80s and so dominating. From the 90s onwards, you had kind of the statistical models or connections models kind of evolved. And nowadays we're kind of evolving also to the foundational models. But instead of seeing those two like realms apart, one of the ideas what the framework kind of what we wanted to introduce is to bring both worlds a bit together and have a more gradual or spectral way of interleaving between both worlds, which is like the between programming, having control where we have logic and everything that we have like from formal languages, but on the other hand, use the power of generalization from like models to find, you know, structural patterns in the data because they're really good pattern recognition engines. And actually this project started off after somewhere like GPT-3 towards ChatGPT in September last year, where when it came out, there were immediately some limitations. Symbolic was amazing, the progress and so on. But still, back then, at least, ChatGPT was not able, for instance, if you queried data that was more recent than 2021 or so, it was not able to, give you a reply on that. And in general, there is actually an inherent problem of, let's say, causality, for instance. People were always saying, like, look, this is no causal structure because it's just statistics in the end. Or, for instance, adaptability, like I said, with the retrieval of information that's more recent, or even if with the limited context size. So if you like try to make a storytelling and then you just evade the context limit of the LLM, well, you will probably forget your main protagonist and everything that was like beforehand. And one of the things that we ask is like, first of all, why do we have to store all the facts in the weight space as well? Because I mean, you don't know all the knowledge of Wikipedia and you don't know all the knowledge of the world and so on, and this updates regularly in the news and so on. So you just look it up every time, and if you're interested, then you maybe look it up multiple times until you memorize it, but actually you know where to look for. We saw this now obviously integrate with Bing and other engines that they're kind of combining these ideas already in the meantime. And we also saw like follow-up publications. So after the release of our framework somewhere mid-January, also papers came out, like the two former, showing that you can basically instruct the models to ask questions about like what kind of sources do they have to query to get the answers from. Is it a question answering a problem? Is it maybe a calculator that can solve this problem, or any other source for the information to retrieve from, and just rewrite the answer afterwards. So basically you get some input, you kind of just classify if you want, so or you should classify the input, and then you basically just select the tools, do the computation, and then just rewrite the answer. And as I said already before, also our lab is going more in this direction of like broad AI, where up until the 80s, like I said, it was like very dominating the symbolic AI world, where we had all these perks that we use today, compilers, everything that kind of the groundwork that was built up comes from that time. But there has been an inherent limitation, obviously, to generalizations. That you cannot, as many regexes and templates as you build, you still cannot really find all the variations of it, right? Now we had this domination, so especially since the breakthrough in 2012, that like, yeah, neural networks are the things, right? So we go just this way. But actually, the path that we're following now is the idea of the broad AI movement. So away from this what we call now narrow AI, just having specialized models for specialized tasks, more in directions of combining symbolic and sub-symbolic systems to rewrite formulations, call engines, do the computation there, and then basically maybe reasoning there, and then basically just give back the answer and so on. And this enables many advantages from adaptability to abstraction, interpretability, and other stuff. And I will talk about this in a second. So the way we see it is that we believe that in the future computational stack is, and we see already some emerging factors in that direction, that models become smaller and smaller. Obviously, GPUs still get bigger and bigger, and then more potent, if you want. So at some point, as the JVM in the Java virtual machine in the stack, and you have this like compiler and so on, we will have at some point every pocket computer, everything will have in some way or form a neurosymbolic engine in there, which you can use, the sub-symbolic or symbolic interactions between both, and then do the computation and get more elaborate results. So you can think of it as a more, if you want, so a semantically averse parser, if you want. So now that would be a very oversimplified thing, but that could be one analogy to the classical world. There is actually a more inherent futuristic view on what can emerge from this neurosymbolic, at least from our perspective, from this neurosymbolic interactions. Because if you think of it this way, if I can borrow the Enrico Parfi's, I think, analogy of software 1.0 and software 2.0, then you had like the software 1.0 was a classical program where you had formal languages, structured data, tables, and all the compilers, things that we see in programs or we program mainly today. Software 2.0 is a more like data-driven approach where we have just raw data, and then we just go end to end, try to learn a function that solve the problem. So we have nice generalization properties. But like a software 3.0 would be this neurosymbolic system. So we're interacting in both worlds and just selecting basically the computation on the engines that are most robust, and then basically using generalization properties to build up, if you want, so a computation graph and then execute that computation graph. So we believe we call this here interaction-based, or we could think of it as instance-based. Imagine I would just give you one example of an object in the visual spectrum, and I give you exactly one label once. Try to learn a function with just one example, it wouldn't work. Also, but still the variation of that sample could be very, very, very difficult to program, hard code something, right? So the idea would be to use the properties of generalization maybe, but the associative power of symbolic systems to combine these two things together. And I will be more concrete in a second. Specifically, what will also be nice is if you can then in the future conceptualize and execute applications at runtime. Think of it like the Van Neumann architecture, where you have central processing unit, random access memory, and so on, and you do the computation and push and pop from a stack, as actually also Leo indicated there. Imagine you could conceptualize a program at runtime. So that means in context conceptualization of a program, and then just execute that program. So if you would just turn off the neural network, if you want, so then the entire program is vanished, because it has never been actually programmed or never had been actually learned that way, just through interactions or instances from the outside world, molded towards the kind of program you wanted. Or if you want, so you could use the properties of hallucination to let's say, if you want the word processor, have a nice tiger skin or whatever in the background, because you just change the code at runtime, because you just ask it to change its representation. So these are things that we kind of see as a future programming stack, and which can emerge from these interactions. Now, the question is, it's nice to talk about that we can conceptualize and execute programs in the context, but the problem here is, how do we control what's happening? Because we can just generate something and then just execute something, but that doesn't really mean that we're getting somewhere. So how do we see this control factor? And assume that we have a generative process here. What we want, or what we see, is basically if we can just take any time step and just verify variables, maybe use sub-symbolic systems to verify other sub-symbolic outcomes and results. We could use that, for instance, or we could use classical, regexes or properties from symbolic AI to really see if X larger than Y, or whatever properties we're verifying, and then if that is violated or not, then we basically just go back, regenerate that with the new condition, and then do this flow until we get somewhere where we want it to get. To be more specifically, maybe all of you are kind of familiar with chatbots, especially now with ChatGPT and all this way of how it interacts with you. For us, it was back then a question: how do they actually sometimes get this very nice narrated or scripted answers back? In some cases, and some not, right? So the way that we, for instance, came up with the idea in mid-January and so on, is like having this kind of narrator instructing. So there's actually a free entity interaction in place. So the user actually interacting with the system, Symbia, which is now representative as our chatbot, if you want so, and the narrator, which is, I think, now the equivalent of system, what you know now from GPT-4 or from the interfaces, what you saw now. So basically, the narrator is just instructing how the actual chatbot is never seen by the user. So it's just instructing how the system should actually respond towards or verify or whatever to leave out or leave in as information. And doing it this way, we can now actually have a very nice neurosymbolic flow control, because if a condition or something that we applied on is violated, we just call another expression, go back, and maybe do another generative path or so. We have just now this ability to just unfold and then verify at each step, or after some paragraphs or whatever we want to define as an interval, the outputs. So to conceptualize this entire picture, the entire framework from our perspective, is basically we have a language model with the language interface. So this could be any, like Lee already teased, type 0 to type 3 language snippets or parts. So we just feed this into the neural network with some instructions, and we will see how these instructions are composed in a second. So based on, let's say we have an operation, we feed it some instruction, maybe some payload from the user, then it computes something, it gives some output, and then we place conditions and constraints on the output. And depending on these constraints and conditions, we might call other operations, say, okay, this was not what we wanted, and make a loop out of it. Or we basically just go to some engine or so, and then they call, maybe there was an instruction to search some facts, so that there are some facts in the input space. So we go for a search engine, and then, we use Google in this case, but you could use any what you want. Or we can use OCR or any other things if there are images or some other things like links or some other things involved in the query. And the question is now, who's controlling all of this right now? It's the user mostly, because he has the world knowledge. But it's not limited to that. You could have, we wrote also some scripts if you want, so some demos you can show at the end, where you have like a knowledge base where you just execute this in a certain behavior. But also in the long term, that's the goal. I think where the most is to gain is this meta learner. You could actually learn this, have an agent controlling this flow and in these interactions, because this is exactly also in line with toolformer and maybe other ideas that kind of merge right now. The question is, how do we prompt this thing, or how do we make these instructions? And there's actually now this formal language plays a bit of a role, how also Leo teased it, because now we illustrate here that this might be some natural language text, but there might be also like a very structured examples, as we always like saw that the few shot examples when we do few shot learning. It turns out that you can actually build associations through symbols. So for us, everything is a symbol, if you can think of it. It could be a number, it could be a string, it could be even a paragraph if you want so. It could be a hash code if you want to associate some, maybe an image behind some hash code with some other object or symbol. So the idea would be to make, let's say in this case, it's a fuzzy equals instruction here, where we say, are the following objects the same? That's like the, if you want, sort of general prompt at the top. And then you give it some few short examples. And what you're kind of shaping right now with this is you're kind of creating like a subspace where you're kind of giving it a notch that 1 is equal to some like string 1. So basically these two things should be treated as equal from now on. 6 is equal to this 6 and so on. Even dates also you can equate, and other things you could basically equate. With the assumption that generalization takes with it, so there are semantic similarities, obviously, between words and between odd numbers and so on. And models, back then we used GPT-3. There was sometimes very well working, sometimes failing. But with GPT-4 and others, it's expected to better and better follow these alignments of these associations. So this is actually very nice now, because what we now create is basically we're having, in a way, these are like, think of it as grammars, but this is just instance based. So we don't know what the grammar actually is here, because it might be very complicated to format the grammar, but we just say, okay, we have multiple instances that we kind of, this is what we want. So we span a subspace, and now from there, from here on, this is how the LLM should behave. And the question is, how do we compose them? So the prompts that we compose is as follows. So if you think about it as a class object, from now programming, like I told you, there is software engineering and machine learning kind of trying to bring them closer together. So we use basically classes as base objects, which have obviously some global attributes. In this case, we call it static and dynamic contexts, which are two variables. So we'll explain this in a second. And then obviously a class has multiple methods. And where they, like, the instructions of the operations are placed in, maybe some examples how we want to manifold that, and even a template if we want to, like, say, like, go from here, from this template structure onwards. And there's obviously the user input with some payload. The payload could be from some previous results of execution. You might be familiar with these things as, again, the system. I think it's now called in ChatGPT or GPT-4, where you have the system prompts. you might have the other ones being the use instructions or the computation of the payload, what you want to have. Now, what is the static context, dynamic context, and why is this fragmented? The idea here is static context is if you have a class, for instance, you can have, like, say, a SQL class, where in the header of the SQL class, there is the static context defined as you are an SQL statement, so to say. This is how SQL is. There's a query language, and there's some explanations. There are like from statements that go to databases. There are select projections and so on. That, you know, you just describe basically what this behavior is of this class. But maybe at runtime or without changing the code, if you want, so you might want to say to the user might say, but you know how about the formatting should be different every time when you generate something, because I want to have a alphabetic or some other ordering or so. So you give it a dynamic context and can just, this is like, if you reset everything, you don't have this anymore. So it's basically at runtime, if you want. So now the other things here are operations, because like I said, a class could have multiple operations. SQL, for instance, what does it mean if I add two SQL statements together? So what was the most logical way to add them? So if I give this problem to a human, he will look at it and maybe like think about like, okay, maybe he wants, like, I see the same tables, I see the same you know, selections and so on, but they're like both are different conditions. So maybe the end conditions have to be like ended, and the where statement has to be kind of combined, right? So this would be an addition maybe of two SQL statements, but you could have any other operations, and there are multiple operations, and I will show this in a second. And this is actually the full pipeline, how we use or how this is composed. So basically we have the user input calling some custom method. We use a lot of decorators. There's a design choice. I will elaborate this later on. There's like basically from the decorator, some pre-processing is called. So all these blue highlighted things are basically how we compose this system-based prompts, and all the yellowish things are basically user prompts or payload from previous executions. And then we have basically just passed on to a preprocessor that can reformat the import, then passed into the actual engine. You see this structure here. This is just one choice of this. You could actually have a prepare statement, and you can change and wiggle around and turn all these things on their head as you wish. So you could have at the end the global context, at the beginning the user query, and whatever you want. It's just subclass the engines, and then you get some output out of the LLM. And now you can basically apply the post processor. So you could like trim off, you know, unnecessary spaces, maybe reformat something into like capital case, lowercase, or whatever you want, and then apply all the constraints and then get the output if everything was successful. Now, why did we choose all this like weird, why do we associate classes and these prompts and so on in a way? Well, there is an inherent property from object-oriented programming actually that kind of is you know, for us now natural, but it's in a way very important because abstraction is built in there. So if you think about it this way, as we have also in PyTorch, so we have module, and we derive from module different individual modules, and then we can derive further on. And any of the implementation in the subclasses can have different behaviors, right? So the behaviors shift based on which class you're right now in. So this is the idea also of having animals, mammals, dogs, until to some specific dog. And if you would like bark, what would it mean to bark as an animal versus what would it mean to bark as a Shiba dog or whatever, right? So these properties we kind of wanted to ingrain into the framework, where we see that at the top there's a symbol. Everything could be a symbol. It could be an image. You could put whatever you want in it. You just have to find if you want to process it by an LLM, have to find a string representation that kind of preserves the information, right? So if it's an image, well, it might be not efficient if you just flatten out the image. So you might want to use a hash code or something else if you want to process with that. But then you basically just derive from there the expression, which adds some functionalities. This was just design choice. And from here, every other class is basically derived from. So you can have a styling expression, you can have a compose expression, templating, and so on. SQL expressions, whatever you want. So this is kind of the inherent hierarchy. And the nice property or idea is here, this propagation of how methods behave. Like I told you, I derive from expression, now as SQL expression. Before I had no context how to add two SQL statements together. Now that just I give a description at the top level static context, now context-based, the addition of two SQL statements makes suddenly sense, or the LLM can at least associate what it would mean for it to do this computation. And now, if we have individual expressions, we can actually, what we can do is now chain these expressions to get together. So what we do is basically like chained operations, where we say that actually, if we have like a query like this, Marvin's has 4 pounds and likes to meow when I pet its fur, for instance, is Marvin a cat? What we actually can do is now take this natural language text and, take the first expression, maybe extract entities and relationships. So basically we extract cat, fur, meows, all these properties from the sentence. We can actually feed that into the next expression, which does maybe a formulate and higher order logic expression from that. So basically it takes in the original one, this context extracted version, and builds up something like a logical expression with functionalities, feeds it in, and maybe then says, okay, now place in the query at hand, execute that, and then basically get a result, and then just rewrite to the result to the user. So what we did here is basically we decomposed the problem that was at the beginning, which required reasoning. Keep in mind that this was at the time of GPT-3, where like reasoning, it was very limited. You could have tripped it off in various ways. So the idea was, how do you make it more potent? Basically, you just decompose it more fine-grained steps that you can verify, check, and try it out, and then basically you come to the solution, which in a statistical manner might have not worked, for instance, right? So that is kind of the idea. But how do you might ask now, how do you know what meows is a function, or what does it mean to evaluate furry? Well, the idea here is that the assumption here is that you have a knowledge base, maybe, of all the functions, a symbolic knowledge base, where you have all the functions defined, either subsymbolic representation or some hard-coded whatever interpretation. And then basically you just have access to that knowledge base, look at it, and also have access to the language model with the instructions, so it can associate which of these things are available, which not. And if things are not available, it says like, I don't know what to do with it, or it just skips it, for instance. There are some limitations, obviously. So the idea now is, how does this fully connect to go around circle with formal grammars, and what is it? Why do we actually need symbolic? Like, why do we need neurosymbolic? This is maybe one question again, because maybe in the future just scale up again data, scale up model, and everything works better. Logic reasoning works better. Well, we still doubt that, because one of the things that also Leo tangented on is basically the memory. So basically, if you look at the paper from here, DeepMind, what they analyzed is, for instance, transformers. If you just have transformers with feed-forward neural networks, you have just a limited attention span, basically, and actually what you can only process is in that attention span regular language tasks, if you want, so regular context language tasks. If you want to have, let's say, context-sensitive languages to process that, imagine you want to write a book, for instance. You might not want to write every time about your protagonist, but somewhere you want to write about it, and at the end you want to write about him. But in the meantime, maybe not, depending on the context, right? Your story should evolve, but you don't want to forget your protagonist, right? Because it just evaporates. So what you need is kind of like an external memory where you can put it on a stack or whatever, and then you pop from that again when you need it, based on the current operations that you're kind of performing. In a way, if you think of it, it's like we humans do. We don't know all the things by heart, but we know where to look it up. And if we need some information now to look the details up, then just go to Wikipedia or whatever, read it there, read a paper, come back, note some details down, and then go from there with the computation that we actually do right now. So, and this is actually a neat thing that it translates to if you want, so the state machines, because there's an inherent connection here. And the way we see it, and this is actually current research that we're doing, is we're trying to equate this to symbolic dynamics, if you want. So where we say that we have this dynamic system, actually, because if you have a neural network and you just chain their operations and just unfold the system, if you want, so you didn't actually want to study its behavior and want to study it's symbolic orbits. So from one symbol, so discrete state to another, how you unfold and you end up from one state to another, basically, with each token that you produce, feed in again in the input space, and so on. There is actually also some work that Stephen Wolfram and so on published, so like some blog post, where he called it like the semantic laws of motion for neural networks, which we find kind of interesting, but it's still like open research, and this is like interesting research that we're also looking at right now. Is there a way to, like I told you, when you condition the model, you kind of create a cone in the space or in the subspace, and if you chain these things together, multiple like subspaces, and you kind of have like a semantic motion. And the idea would be to have a way to control this path that we're taking, because now we can, as I said before, conceptualize a program and still have like guarantees where we're moving through the program, and then like execute a very, very structured way of this program. But so far, this is how do you measure it? There are multiple open questions and research problems here. And now to take this again, this picture in mind, and I said that there's a meta learner here involved, right? So how does this actually look like? Well, the idea would be that there is an agent that can, in its current attention span, work and by some instructions or do some operations based on some context with the neurosymbolic system, and then basically do the computation of, let's say, a very large data stream, and push and pop from some external memory. So it could be a knowledge graph, it could be whatever external memory where it kind of like pushes information from, but it kind of knows a key or so how to retrieve informations again, right? It's like the same way when we store information, we save papers and whatever, we kind of know the titles, the authors, or some property, we know that we can retrieve the information again. And what I, for instance, don't do anymore is paper, pen and paper, because I cannot search there, for instance, and all the notes are usually lost if they get too large. So that is how at least I or others operate. And this is like the idea: can we train and optimize a meta agent that can also learn to do all these interactions, select the tools, and how to store and retrieve information? This is, I think, valuable research that is also eased with our framework. And now everything from here on is going to be just practical examples. So it's basically, how does the framework look and work like? So we have this operations, as we see here, for instance, and I told you there's a base class symbol, and symbol has already some default operators implemented. One of them being this AND operator, for instance. So if you have two string expressions, like the horn only sounds on Sunday and I hear the horn, then you could have like an implication. So there are multiple examples how implications might look like. Sorry. And the result out of this computation would be it is Sunday as an implication, for instance. Sorry. Another one was the sorry, for fuzzy equals example, where we have I just caught a cold a few days ago, so sorry. One is smaller and equals to 1 in a string form, which is evaluated as true. The other one would be maybe equating numpy with some approximation of pi. So what basically will be evaluated here, everything that is not a symbol will be converted to a symbol, and then prompted and composed together in that the LLM can process this. So when you say like 3.1415 without any further context, the most assumable thing would be that this is pi, probably, if you would see that even as a human, right? So without any other context around it. Other things which are very interesting, which you maybe also saw with AutoGPT and so on more lately and got quite hyped, is like a try execute expressions. So what you have here is like an executable code. This is the execute expression, which just runs code. And the try expression, which catches code and like re-instructs and analyzes the results. And, if something goes wrong, sends it back to the LLM. And obviously you can chain these things together. So the idea would be, if you have some, let's say like this syntax error prone code here, then you try to do this cast, which will fail. When you evaluate this, basically, then it tries to reprompt and say, well, this is the cast failed. So what is the most viable solution? And then it will manage to figure out that the comma was wrong placed and so on. And also one of the most prominent or known examples is in the word2vec example with king minus man plus woman, but in the vector space, or like in the embedding space, how we do this computation, which is kind of hard to interpret, right? So the idea was, is it possible to create prompts or instructions that kind of, without having this specific example in there, to create something like that, that this computation becomes feasible or understandable for the LLM, and it at least works with some similar examples, princesses and other things. There is also now, how do we construct custom operations? It's actually very easy. So this would be like how we use our equals, or fuzzy equals operation. We use actually decorators for that. Why we use decorators is because we want to leave always the implementation part available for the user of our framework. So actually, if the LLM, for instance, doesn't work right now or is not available or whatever, then there should be always able to be a fallback on classical code. So you could just have the implementation space empty. If you implement something there, then the fallback is the implementation. If not, then an exception is thrown through. That's kind of the philosophy here. And how does this look like? It's basically equals is just a more specific version of the few-shot decorator, where we have prompts as the most elaborate string here, and then like different kind of prompts with examples. A list of examples that are basically behind that. We can have some constraints put on this, which are callables. We have defaults. You can also define a default in the decorator directly instead of having an implementation. Some limit of how many results you might want to get back. The pre and post processor, which you saw in the pipeline, how this is executed. So this is basically the whole magic behind it. So what you can now do is there's also a zero shot, which just has no examples with these constraints. So if you want to get a random int generator, I don't know if it's feasible but just as a demonstration, you can just instruct it like this and put some constraints on it, and also the return type is a constraint. So basically, it makes it very easy to just say one annotation, some examples, or it's just a constraint, and then just this is how the LLM is instructed. You might ask now, what's the difference maybe to LangChain or any other things that it can do? Well, my question would be also in the directions of, I mean, you can do everything with C maybe nowadays, right? You don't need Python or any other higher order languages, but the amount of metacode that builds around the same thing you want to just execute maybe with one line in Python might quickly explode in dimensions if you go down to C or to even to further down the alley, right? So basically, this is one way of how we also see it. We want to have at least metacode as necessary. And the easiest way to just instruct or create functions and expressions that really do some specific task, like generating Japanese names and with some limitations, constraints, and so on, maybe even with some dummy implementation if the model is not available. Yeah, the one of the last things, just 2-3 more examples, and I will cut it. Are, for instance, we can build streams. I told you that we want to have the stream of if we have a larger data set that we want to process, which is larger than the context of the model, what we kind of came up with the idea is to chunk it up, right, and do stream processing similar in a way to PyTorch, where you can open a sequence of operations, right? And then now each chunk is independently operated with this sequence, and then afterwards you can cluster things together again or do other expressions, or even chain together, like I told you. You had some computations prior to that, and pass in a payload, and query that payload if you, for instance, want to ask for something from an OCR text. Yeah, we have also a lot of many tools. Yeah, you can look at it if you want, some shell tools which you can play around with. This was the SQL example that I showed you or explained to you earlier, where you have the SQL class, an object from the SQL class. Now you pass in natural language text, and the cool part is it just converts that to SQL, but now you can do operations on that result, that query, right? So what you can do is shift information in where it's contextualized shifting, not just appended or so. So it basically knows now, because it knows it's an SQL expression, how to contextualize and convert that into this expression. And yeah, and then basically maybe subtract information again or convert it even to other query languages. This is how we actually have the basis, the conditioning for our chatbot that is also a bit baked in there, where you can maybe separate between things like mathematics, where we call Wolfram Alpha, where we can separate between linguistic problems, or maybe, I don't know, search engine requests also, where we make conditions and just, you can go as fine-grained as you want. So we just use this is instance of, and then ask if it's instance of mathematics or something else. And then it basically just, you know, goes into that path. And then from there we can rewrite the statement in a way that is maybe compatible with Wolfram Alpha or something else. This is the example of the chatbot, which is just like Symbia, which is easily derived from chatbot expression, which is from expression derived and so on. And there is a nice function in there, narrate, like I told you before. This is how you instruct it to just tell you what it wants you to tell. So the user interacts with the system, and this is how it narrates back. And if it does some computation, like chit chat or math problem or so, you can pass it on a context, a payload, and then it will just rewrite that information. And these are basically the options. So you use actually also the in-context few short examples to classify the input. So that's also, you can dynamically grow this list or whatever you want to manipulate the list. So you actually can expand the capabilities of the model at runtime. That's one of the things that I told you before with the conceptualizing and growing the application. The question is who steers that right now? That's where we're heading at, saying that we want the meta learner to learn this kind of behaviors. And if you go full circle, you can make very elaborate expressions, generate entire news websites, summary websites. This is from CNBC, where I just fetched the data from the URL. It's like 18,000 whatever tokens or so there, because it's like just a dump of the website. But then I summarize everything because I stream process it, cluster things together again, because you want to have related news at the same spot, and then compose new text template. So I template HTML first, and then I do a styling. So this is how you could generate an entire website really on spot, how you want it, and not just having like in ChatGPT, if you ask it, you might get some text at the beginning. You have to go back and forth all the time to get where you want to get, right? Yeah. And the neat thing about this expression would be also you can trace and debug, because what you have now is this chained operations, and you can look at even like a stack trace of what kind of operations happened there, right? And how this was executed. Yeah. Thank you for bearing through and for your attention. Sorry for taking a bit longer than expected. And looking forward to questions. Hopefully there are still is time for questions.
Yeah, thanks, Maurice. I think we can leave it at this slide so people can scan and see your repository while we do the Q&A. So maybe we have 15 to 20 minutes of Q&A. I just want to highlight whatever workflow that Maurice described actually bears striking resemblance to AutoGPT. Like you have a starting task, you break down to subtasks, use the neural symbolic architecture to find the right tool to use, then proceed to use the tool, and then after that, go back again to the engine, find what's the next tool, and so on until you solve it. So the way that they process the symbols here, they kind of use the LM few shot or zero shot prompting to decide like what symbol to use and like whether the symbols are equals to each other. So I think that's quite interesting. So maybe I would like to just ask the first question first, while the rest of y'all can think of the question. So my question is quite simple. Like, why should we go into the symbol level as compared to just, you know, describing what you want into a large language model like ChatGPT? Why do we need to bother with extracting out the symbols and putting those symbols explicitly into the code, like your code? So maybe you could give some insight.
Thank you. Great question. So the thing is, what we see is you want to have control. Like reasoning is one of the main points, right? That we are also heading towards. So we have nice reasoning engines. We have you know, symbolic solvers and all the stuff that we developed. You know, the entire history of computer science. So now we're just kicking everything away, and we're saying like, we're treating now large language models like oracles, right? We give it one query and hope that the best, like the result is what we get out of it is correct. But if you think about it, you can create many very complicated statements, and then you see that rules can trip it off, and then, you know, because there's no reasoning really baked in. It's like part of it might emerge for statistical, you know, representations, but you want to have control of your program. So specifically now, if you go in directions of automating these things, so you don't want it because it's just right now in the data set, there was a weak connection between two types of associations. It just, when it sees that word or so, you prompt it that way, then you basically just end up A-walking the model with all the results. And imagine you have like a very elaborate computation, which goes in many loops and so on, right? Your entire application, quote unquote, crashes then, right? So the idea here is to kind of bring both worlds together, and having these objects and symbols that we can, especially for abstraction and so, that we can assign to and say that these are kind of related in a way or another. And then we can verify also on them, right? Because you can say, like, we have these symbols now in the system. Are they related with the systems that we can verify, like now how we actually do it? When you have a formula, for instance, when you do, you're not a walking computer. I'm not a walking computer. I cannot do the square root of 1.375, whatever, in my head. But I know how to write. If I tell you this in a textual form, I know how to rewrite it in the formula, use a calculator, and then I can verify the results and everything, right? So I can see that the computation worked. And I don't have to hope that the LLM kind of worked with it properly, right?
Yeah, thanks. So actually, I played around with this architecture quite a bit, and I talked to like the Symbia, the chatbot. So it's quite cool because you can literally just type in anything, and the chatbot can infer in the right like symbolic architecture. Like if you want to do calculation, it can refer you to Wolfram Alpha, maybe like solve some quadratic equation. You're gonna find out like what's the weather in Singapore. I tried it out. You can search the web and get the information for you. So there's some benefit of grounding it in symbols because I mean, in this case, symbols can also be tools, because in this case, a symbol can encompass the entire tool, like for ToolFormer or like Visual Chat GPT, we talked about tools back then. One symbol is actually a tool, but more importantly, this symbol can also be those kind of logical inference kind of symbols. You can run logical inference tools. You can also use like calculators and so on. So it is very, very versatile, the whole notion of symbols here. And you can just program in whatever you want. Like you can, so I myself, I played with it. Yeah, so I think it's quite interesting. Oh yes, sorry, and anyone was talking?
Maybe also from a physics perspective, just to also give you this, if you have a physical system already, you can basically couple that and associate that and use that engine where you do the computation, where you have everything like worked out in the simulation of the physics system and come back to the language symbolic representation.
Okay, yeah, anyone else would like to ask? Maybe you can take 3 to 4 questions.
Hi, I have a question here. First, thanks for the presentation. So I just before the question, I just want to check my understanding first. So if my understanding is correct, so here you have to hard code how do I, for what kind of tasks, which kind of let's say we have interface the language model with different plugin. So different, maybe symbolic way to solve problems. So here we have to hard code for what kind of problem I need to use, which kind of plugins. Is that the case?
So thank you for the question. So for now, if you want to interface with some system or so, obviously you have to implement it, because there is no system yet learned that can automate that process. But the idea, of course, on the long run would be that, imagine you could give one of the subroutines you could program as an expression would be read an interface, read, for instance, a documentation and so on, and connect the best way based on this condition, on this context, try to find functions that best interface with that documentation, right? Like trying to post something on social media and then just reading over the documentation of the Twitter API and then coming up with functions. So, but what you need now is, we need to have, first of all, data sets. In our opinion, we need data sets that kind of are not like I told you, we have right now data sets that usually get a prompt as an input, and directly we try to infer the answer out of that. So this is how we treat the ChatGPT for a long time, where we just give it a query and then like the most natural way to answer that, and we put all the information in the weight space. What we now need is something like more data sets that kind of have these thought processes, this what we then can train a meta learner that kind of follows these thoughts, this chain of thoughts. When I want to program a website, for instance, I think of, okay, which programming language, okay, where do I download the newest version? And there are many questions that I ask myself. Is the specification detailed enough? Do I have to ask my client back and then ask him again, hey, great, what kind of website is cooking, whatever. And you know, after I've worked out all these questions and answers to it, so I put all of these things on a stack, if you want so, then I go from that, and then I go trial and error maybe with some things from Google, try the template and so on, and move forward in this way. But we don't have models that do this kind of stepwise thinking, first of all, and then like trying to work these things out. And in this way, we kind of need data sets for something like that, in my opinion. And we need then ways to isolate the systems to trial and error execute stuff, because I don't want to have a model AWOC on my machine with hardware with access to my SSD or whatever, where it reckons my entire system when it tries things out. So this is like things that we still need to develop.
Yeah, so the reason I asked this is because one of my concern is, if we, let's say in the future, when the large language model become even more capable of solving complicated questions, then maybe for some question, it is even not clear what kind of tools they need to use. So maybe we have to let it to even strategize how to, or even select what kind of tools to use. So if that's the context, then I don't know. Like I feel like explicitly telling them what to use, in which case might not be very scalable.
So yeah,
if I may,
yeah.
I was going to say
if I may,
the plan to build a strategy, right, to attack a problem piecewise. You mentioned the lack of a proper data set. My working model is enterprises and so on. And they're very complex beasts. Nobody really knows how they work. What kind of data sets would be appropriate to come up with those complex plans for a largely poorly understood environment, where you've got these symbolic approaches, call them APIs, call them applications, people, processes, whatever. But how would you break that down? How would you represent that as a data set that you could approach that problem?
So what I, for instance, liked was when I watched Open Assistance, for instance, video with Yannick, for instance. He kind of, when he went and showed up basically how he collects data now with their framework and so on. But what I liked is when he was like asking some question about Red Fox and some property, what it can or cannot do. I forgot the details, but the point was he was asking himself all the time, sort of a self-ask if you want so. Wait, what can it do? What can this Fox do? And then was going on Google, going on Wikipedia, and all this thought process that he actually put in there is in the end lost, because what he had done is the result basically was just the input of the prompt, basically what was the original question, and then the output was the most elaborate answer to that question. But that intermediary, that thought process, that chain of thought, if you want so, that is kind of the data set that I am still vouching for, or I'm vouching for, that we can use that as a conditioning for the models to come up also with these logical thoughts. And also, why I say also this, why do we tie this so tightly together to these expressions and this object orientation? Because there are also relationships baked in already. When we think about object orientation, we have this abstraction of interfaces and then the more and more concrete implementations. The properties that emerge from the more concrete implementations are in a way reflecting what we actually think, how we abstract the world all the time. And we need maybe this bias also somewhere in our data set, that we can say this is more abstract version of this data set and so on. So this might be also a property that we bring in abstraction in a more profound way.
Thank you.
Sorry, Leo, you wanted to say something?
Yeah, I think to can you hear me?
Yeah.
Yeah, initially before Richard asked his question, there is this problem of open-endedness, which touches exactly what I haven't seen his name, but it's exactly what open-endedness touches, which is to say that you can explore, so you penalize more the exploitation, and you leave the exploration phase kind of unrestricted to come up with different behaviors. So you can try to, for example, the way I imagine this is like the way you would SSH into a virtual machine. So in that virtual machine, you have like a reserve space of what you can do ultimately. So you would not broke your system into there, but you can, for example, open something like a virtual machine, and inside that virtual machine, you can basically let this open-ended process to explore how it come up with different, I don't know, what tool should it use and so on. And you just catch those expression. If your virtual machine dies because it did something stupid, you just restart it from scratch. So you won't lose anything. So this ties a little bit to the point of running simulations. The simulations you cannot break in a way, so that's very useful. So this is the way I think about it, and probably somebody at some point will actually take this exact idea to use virtual machines to run these things in that virtual machine, which you cannot break. So yeah, and the second point to add to what Mario said to you, Richard, there's also this new model, Dolly 2, which was basically a model trained on instructions, to follow instructions. You can think of it as being a similar problem. So reinforcement learning through from human feedback, it's a very powerful technique. You can apply it everywhere. You can apply it to even build a data set that would display this capacity of chain of thought that Marius talked about. Nothing stops you from doing this. It's like all you need is to annotate this data. Now, someone will do this. I mean, you will be interested to find out if it works, right? So you have all the tools. You have Instruct GPT paper, the way they train the GPT models, and so you have everything. You just need the data. And obviously, why would be chain of thought? I mean, in terms of an assumption that you can make, why would be chain of thought different than following instructions? After all, a chain of thought is like a meta instruction. It's like the what Mario said that Yannick did was basically a metacognitive aspect, right? You ask yourself questions. How do I get unstuck? What should I do here? These are all things that you can capture in a data set. And you can even put domain expertise, right? Because obviously it is different from a lawyer to a programmer. A programmer would do things differently. A lawyer would do things differently. A medic would do things differently. So you just add domain expertise from each one of these domains, from physics, from math, from everywhere, and you just build this chain of thought data set. This is obviously possible. It's just a matter of, I would say, time until people, probably OpenAI is already working on this kind of stuff. But again, you need a domain expertise. So you have to tackle it one domain at a time. You cannot take all the data. You just, let's solve code first, right? Because code seems the most accessible. Then let's solve law, then let's solve, and so on. Because you have this neural engine, which is very powerful. You already have it. You just need the alignment to whatever your task is going to be. So in my case, I definitely see this possible. It's like probably just under the corner.
So one more thing to also to that, why? So you saw, so from the previous image that I showed you, where you had like the language model, but then also the meta learner having this chain of thoughts. You can also think of the meta learner as kind of operate at different timescales. So, because the problem of the language model is just, I mean, it has to follow instructions, right? But it has no, how do you verify the output? That's one of the largest problems here. Because imagine if it's the natural language text. So how do you verify natural language text semantics, right? So what a meta learner, for instance, could do is basically set times like goals, also milestones, having where you want to generate to end up in the end, right? Some intermediate steps and so on, and maybe the next, operation that you execute. And then you basically just verify if A and B are associatable, right? And are kind of connected or not. And if not, then obviously the meta learner, like we would look at a result and say, wait, this is kind of off. It's not what I would have expected, right? From the computation. So that is something that also I think is necessary for a data set and why I believe two RLHF differently trained models. One just follows instructions, the other one has like this guidance and strategy and planning as a baked-in data set.
Okay, maybe I read out a question from Evan. He asks if he wants to implement natural language processing questions in symbolic AI. For example, like he's very interested in syllabification, like to split a word into syllabus. How can he do it in your framework?
You mean like just creating an operation? That's using basically the decorators, as I showed earlier. So just creating syllables, basically, I would just create an expression just derived from, in this case it's symbol, but you could derive from expression and then basically just give a few shots or examples how you want to instruct the model to behave, and then you can have it as an input. Because also the input is variable, the definition of the decorators can vary. There's in the documentation, I think, many examples how they show them how you can create such instructions.
Yeah, you just replace, in this case, get random integer with get syllabus and so on, and you just have this prompt that would guide the model on how to do syllabus. And this shouldn't be a hard problem because you have basically the way GPTs were trained was using a BP encoder, which is a way to chunk and segment words and keep parts that are more common. So this should be a very straightforward task, I would say.
Maybe even as a comment here, because maybe this is already one of the things that already would benefit a lot if you have data sets in this line of thought. Because I kind of like his question. It is not guaranteed that it works. It's basically few-shotting a model, hoping that what you are querying it is aligned with somewhere in the data set of the RLHF, right? So if you want the first steps, how to improve also not only our framework, but in general, alignment with how, like, let's say we have now this hierarchical structure of symbol, expressions, SQL, and other properties, and all of these like operators that are baked in there should behave in a certain way. So if I would tell you add two strings together, you probably thought would be just concatenating them. If I would tell you add two SQL statements together, like I told you before, you would say that's weird to concatenate two SQL statements. So probably if you look at the individual properties of it, you would say, okay, maybe he wants to just add the where clause in a meaningful way. And these things are queries that can happen and work well if it's abundant available in a data set, but doesn't have to always work well because maybe the association was never built this way, right? And there are many cases where we can probably slip over many models, even GPT-4 and so on, which is more capable than GPT-3, what we had back then. So that would be already the first step. How would you approach a more elaborate data set to follow these alignments that even understands these abstractions and operations at different levels of abstraction, right? That would be already one of the data sets that I would wish for.
Yeah, and to add to what Mario said, for example, you have this context that each large language model has, right? And there is work that basically came up with evidence for the fact that you can, reinforcement learning from human feedback is a way to align your model to human preferences. So you can view that thing as a semantic prior, right? But they found out that with the context of this model and the way you are doing in context learning and the few shots and zero shots, and especially the few shots in which you give it example, then there is it's a very likely thing that you might observe is that you can basically shift those semantic priors that were initially put into the model. So actually, you might literally escape from those semantic priors. So you probably saw a quick example here. You probably saw what happened to Sydney with Bing's chatbot that you can access right now. At the beginning, there was a guy who came and he basically just through the way he prompted the Sydney, it just make it reveal the entire instruction set. So that was a way to basically shift that semantic priors, which was actually exactly those instructions in which you could find out that you shouldn't reveal this information to any user. You actually bypass that and pull that information out. So within context, you might be able to shift those semantic priors that Marius said they are induced through reinforcement learning from human feedback. It's possible, and especially with larger contexts, as we would get with GPT-4, it's 32K or something like this. It's even more likely so for you to shift that initial priors.
All right, I think this is a good point to end because we kind of overshot already. Just want to highlight, so this symbolic AI framework is still not complete. There's still a lot more improvements that could be made. If you all have any interest to help to make more like symbol interactions to interface with more engines, right? Feel free to contact either Leo or Marius, and then we can build on this together. So this is more or less like an alternative, I would say, to like the current auto GPT models, LangChain. I mean, you also can use tools. It interprets the output in terms of like symbols. You can interface symbols with each other using some large language model to guide it to see whether is it fuzzy equals, or in the NLP case, you can add in some few shot prompting using LM to like generate the syllabification. So at least that's my understanding. That's correct, right? Yep. So if you all like to contribute more, feel free to scan this QR code here and help to contribute to the repository. If not, I would like to thank both Leo and Marius for the very interesting presentation today. And yeah, if you have any questions, feel free to let me know, and I'll just refer to both of them. All right. If not,
thank you for having us.
Yeah, thanks so much, and I'll see you.
Thank you, John. Thank you. Bye-bye.
Bye, everyone.
Bye. Thanks for presenting.